club day? It was hilarious. Johnny got to see me really angry.
What happened?
I was like
Who made you mad?
almost yelling.
Who made you mad? Are you joking? Do we have to do that?
Almost. Huh?
Like, even if it was like obviously the like wrong answer, you would still argue.
Was it Christian?
Yes.
Oh God.
This argument was just.
What were y'all arguing about?
I was trying to argue. He wanted to look at some test stuff.
You get an extra point.
That argument was credible, but the majority of his arguments were not credible. Well, I prematurely swallowed a piece, and I was going to try to pop it back up, but it didn't feel like it, so I just forced it down. Okay. All right. What have we done so far in chapter 13? What have we talked about?
Light dissolves light. I remember that.
Light dissolves light. What's the very first thing we talked about?
Solution.
Let's put our phones up. We talked about solutions. What about them?
The solute and
Saturated.
super
Yep. Saturated, supersaturated. We talked about yesterday. Saturated solutions. And we talked. I showed you that simulation where, as we put the solute and the solvent, the undissolved solute was a one-way process, and it kept going into the solution until there was the opposite process that started to occur, and that's that equilibrium. So when the rate in the forward direction is equal to the rate in the reverse direction, that dynamic equilibrium was established. That's when the saturated solution has been reached. And when you're talking about solubility of substances, you're talking about, I don't know if I put this, I might have just put it in the AP. When you're talking about solubility of substances, you're talking about the amount of solute. Oh, hold up. Nobody told me. Y'all don't see this because I don't have y'all first period, but every single day when my computer turns off, I've got to redo my settings. I contacted, I don't know. It just resets itself, even though I put it to where I want it. I don't know why it does that. No, it's too much work. It's like energy that doesn't need to be used in that way. So if you see solubility of substances, which you're going to see that today when we get to Henry's law, the amount of solute needed to form a saturated solution in a given solvent. What are the units of solubility? Right, so it's essentially, if you kind of think about it, it's really the units are in concentration. So just keep that in mind. And then what we left off on yesterday is we were talking about how different solutes, just being able to decide kind of qualitatively whether this solute would dissolve in this solvent. And we did that based on the similarities of intermolecular forces. And then I had y'all start working on your practice tests. So remember we did 1 through 17. Yeah, we can go over it. So if y'all get that out real quick, I wasn't planning on going over it, but I think it would be fitting. All right, number 1. The process of solute particles being surrounded by solvent particles is known as huh? C as in Canada. Number 2, pairs of liquids that will mix in all proportions are called A as in apple. Huh? An ant. Number 3, the phrase like dissolves like refers to the fact that B, polar solvents dissolve polar solutes and vice versa. B as in baby. 4, when solutions of strong electrolytes in water are formed, the ions are surrounded by water molecules. This interaction is called A as in anion. A saturated solution, number 5. So C contains dissolved solute in equilibrium with undissolved solute. And number 6, you're just elaborating on what equilibrium is. So number 6 is D as in, diaper. Number 7, unsaturated solution is one that C has a concentration lower than the solubility. C as in, I can't hear him. Huh? I still can't hear him. C as in cauliflower? Cowboy. A solution with a concentration higher than solubility is E, elephant, is supersaturated. Number 9, now we get to the solubility dealing with intermolecular forces. So the principal reason for the extremely low solubility of NaCl and benzene, so benzene is not polar, it's a nonpolar substance, and NaCl is going to be ionic, so when you put it in a solution, it'll break up into ions, well, if it's in the right solution, that is. So in this case, it's not going to break up, and why would it not break up? What's the best answer there? D, so weak solvation of sodium and chlorine ion by C6H6. So Johnny, why is it not C? Why is it not C? You asked me this during club day.
Oh, I asked why it was.
No, you pointed to C.
Oh, I did.
And then we went into this long discussion, or short discussion, of why NaCl wasn't a covalent bond. Oh, okay. But boy, you remember that other stuff, didn't you?
Oh, okay, sweet. That was fun.
That was hilarious. All right, number 10. Which one of the following substances would be the most soluble in CCl4? So, D, good. D as in? Dipple, dipple. 8. Which of the following substances is more likely to dissolve in water? A. As in asinine. Number 12. Which of the following substances is more likely to dissolve in methanol? Good, D. All the other ones are nonpolar. 13. Which is more likely CCl4 again? More likely to dissolve, yes, A. That's the only one that's actually nonpolar. All the other ones are polar or ionic. 14. Which of the following substances is more likely to dissolve in benzene? D as in dangerous dog. 15. Which of the following is more soluble in water? A. As in I never can hear him. Roy, what'd you say? Okay. Number 16, which of the following choices has the compounds correctly arranged in order? A, good. So essentially you put them in order of increasing intermolecular force. General increase. Okay, last one. 17, which of the vitamins is water soluble? Well, ADEK, ADEK is non-soluble or is fat soluble. So the only one that's left is B. And that's why if you ever take your B vitamins, so a lot of times if you look at your vitamins, the daily percentage is way over 100. That's why. Water soluble. Y'all ever done that? What? Y'all never looked at the vitamin daily percentage for the B and seen it's way over 100%? Yeah. Like when you get, I've already talked about this, but when you get sick, a lot of times you take a higher dosage than normal, especially I think it's vitamin D3 is pretty big for immunity, and obviously C. Okay, that's it. So now we're going to go on to stuff for today. So this is what we did yesterday, talking about factors that affect solubility. Intermolecular forces was one. The next one we'll be referring to a different type of solution. So gases in solution, something that can affect the solubility of gases in solution is the molar mass. So larger molecules have stronger dispersion forces. So that makes sense. As you have stronger dispersion forces, you would have a stronger intermolecular force, which would pair up well with a strong hydrogen bonding that occurs in water. But this is what we're really going to focus on today is pressure. So the solubility of liquids and solids does not change with pressure. However, the solubility of gases in liquids does change with pressure. Makes sense. So if I have a solution, and I'll leave it there for a second for people who want to write that down. So if I have, and that's all on one note too, but if I have a solution and, or actually better yet, if I have a 2-liter Coca-Cola bottle, do y'all agree there's carbon dioxide in that Coke? And so it's dissolved in the Coke, and inside that container, you have a certain pressure of carbon dioxide above the Coke, but you also have dissolved carbon dioxide in the Coke. As soon as you open up the the bottle, what's the first noise that you hear? A fizz. What is that fizz? All the carbon dioxide coming out of the solution into the air, you have decreased the pressure on top. So there's a direct relationship between the partial pressure of carbon dioxide on top of the solution versus the amount of carbon dioxide that's soluble in the solution. So have you ever seen those little tops that you can buy at Walmart that you can screw on the 2-liter bottles and you can pump pressure back into the bottle? And so it takes the carbon dioxide and puts it back into the solution. Have y'all ever seen that? Y'all ever done that? It keeps the Coke from going flat. Nobody? Just go to Walmart. It's not that exciting. Just go to Walmart and buy a little thing. So when you get your 2-liter bottle of Coke and you don't want it to go flat, you want it to last longer and have that the carbonation, you have to pump air back into the bottle. And it goes directly related to Henry's law, which I'm going to show you how to quantify that. So Henry's law, there we go, right there. All that carbon dioxide is put into the solution to give it that carbonation. People like carbonation. I'm not sure why. I wonder who invented that. Who invented putting carbon dioxide in beverages and why? But either way, there is carbon dioxide gas on top of this solution, and there's carbon dioxide gas dissolved in the solution. And as you change, the whole point here, she's unscrewing the top, and the pressure has decreased. As soon as that top comes off, the pressure decreases, so therefore the amount of gas that's soluble in the solution is lower. It all comes out. So if I want it to go back in the solution, I'm going to have to buy the special top from Walmart and increase the pressure inside that bottle again. So here's Henry's law. It's just a simple equation here. S is the solubility of the gas. K is Henry's law constant for that particular gas in that solvent. And P is the partial pressure of the gas above the liquid. So once again, as you increase the pressure, you're going to increase the solubility of that gas in the Coke bottle. All right, so let's just gonna zoom out a little bit just so y'all can still see that equation. Let's see if you can try to work this problem. So it says calculate the concentration. Now remember what I said earlier, solubility is going to have the units of concentration. So another way of saying that is calculate the solubility of CO2, but in this case it can also, you can see that used interchangeably. Calculate the concentration of CO2 in a soft drink that is bottled with a partial pressure of 4 atm over the liquid at 25 degrees Celsius. The Henry's law constant for CO2 in water at this temperature is 3.1 times 10 to the negative 2. So just plug it in. You've got the constant, you've got the partial pressure, and so then you'll be able to get the concentration. You can also look at the units here. Moles over liter time ATM. If I multiply by ATM, I'm just going to be left with moles over liter. So if you ever forget the formula, just think about it in terms of unit cancellation. Who invented carbonated drinks? Joseph Priestley. 1767. Club soda, soda water, sparkling water, bubbly water. But why? Priestley published a paper titled Impregnating Water with Fixed Air. Okay, what'd y'all get? Gotta work this out this morning. So we have. Oh, frozen. So Henry's law of constant, 3.1 e to the negative 2 mole over liters times ATM, partial pressure for ATM. Okay. ATM cancels, and you have your final answer of 0.124, but it looks like we have two sig figs, so I'll just leave it as 0.12 mole over liter CO2.
So that's all you have to do.
That's it. How easy is that? Actually, temperature does matter. That's why they put it in there as a tabulation, like I was just saying, just to be correct. But you don't need to know about that now. So what I want you to do is kind of take a, oh, actually I want to, just going to throw this at you real quick. Wait, you'll learn in a second. So there's some book problems, and I went through them just this morning to kind of see which different types there are. 5 through 30 deals with your intermolecular forces and solubility sort of stuff. Very similar to what we did with the practice test. 31 and 32 deal with Henry's law. 33 things. Okay. 37 through 52 are just concentration. Those are the kind of book problems just to knock out and get out of the way. So we have done all of this up until this point, so I just figured we could go ahead and get started on some of this and knock some of these out. Now, real quick, do I need to go over concentration again, like molarity, molality, percent mass? Okay, so if I'm looking for percent mass of a substance, let's say it's substance A, all I do is mass of A over total mass times 100. That's it? Okay. Here's another type. You might see mole fraction, which y'all know from the last unit, or gases unit, that is. So mole fraction, capital X. So you're looking for mole fraction of A, very similar to mass percent. So you have moles of A over total moles. So it's in moles, not mass. And you don't multiply it by 100. It's not a percent, it's just a fraction. I think that's actually on your periodic table. Molarity, so moles of solute over liters of solution. So that takes into account the entire solution, solute and solubility. And then molality, which will be important when we talk about colligative properties, just as boiling point elevation, freezing point depression. You'll use molality in a lot of those calculations. So molality is different from molarity in that you don't have liters of solution, the total, both solute and solvent. You have specifically just the solvent, and it's in kilograms of solvent. Right, so mole of solute. Now remember, molarity is little m, molality is big M. So mole of solute over kilograms of solvent. Some of these concentration questions are a little tricky. So they're not as easy. Some of them might not be as easy as you think. You're going to have to do some maybe density sort of conversions in here. Absolutely. Okay. Questions? It's 9 o'clock. You'll have a full 20 minutes. 20, 21 minutes. It's going to take you a minute to get your stuff out, so I was like thinking about that. Well, some people it's going to take about 10 minutes, unfortunately. Just kidding. You have the opportunity. Hold. Well, hold up. And just a FYI, I'm going to be adding a few questions because at this point, I have these are all your book problems, and I'm not done. I'm not done teaching. So there's four more. There's four more after this one. Gary, four more problems. We'll talk about it later.